Hey everybody, welcome back. So today I have something I want to show you, which is the Turing Machine sequencer kind of random voltage generator from Eurorack implemented in Macs. So this device is really cool. There's a lot of really good videos on it to understand what it does. I'll put links down below. But basically it is a sort of a random number generator that works using what's called a shift register. And I'll show an example of that. And you can use it to create sort of tempo synced or clock synced series of values that are random. But if you turn this dial all the way to the right or all the way to the left, it'll basically loop kind of the last sequence of random numbers that it produced. So it gives you the ability basically to kind of explore and find a really cool sequence and then lock it and kind of keep that. And even as you move this dial sort of towards the edge, the amount that the pattern changes basically kind of on each revolution of itself reduces. So the closer you are to the edge, the more kind of repeating stuff you're going to get. When you're in the middle with the dial at 12 o'clock like it is here, it's completely random. There are also these expander modules, several of them that go along with it. This is one. And we'll talk, I guess, as we get into the patch here a little bit, how all of this works. If it might actually make sense for you to just watch this other video by Mylar Melodies. I think is a really good one where he explains it if you really want to know. Otherwise, maybe you already know. If not, whatever. Just hang around and we'll get into this. Okay, so let me just show an example really quickly of this thing like in use off the bat. So I have two of these. The one on the left is sending notes. The one on the right I'm just using to send a little bit of modulation as a CC into live. And so you can see here I'm sending MIDI from Max 2. That's the MIDI destination. And then inside of live, I'm receiving that here on the first channel. And we're getting this melody. If I put this dial at 12 o'clock, which is that big knob, you can hear I start to get lots of randomness. And I've actually put a scale object in here in Ableton just to constrain things a little bit and make them sound a little bit more musical, even as we generate series of random numbers. And you can see there's these row of LEDs along the top here. And we'll talk a little bit more about what these mean. But there's two things I'll tell you right now. The first is the events are occurring when this first light is lit. So that's how that we know. If I grab this, that we have an event. And then these lights, we can think of them as zeros and ones, producing an 8-bit number. And if you've watched the binary beats video, which I'll put the link up above, you'll understand this. We're basically constructing a number from 8 bits, and that is used to derive the MIDI note. If I move this all the way to the right, you can see that we're looping an 8-step sequence, and I can reduce the length of that sequence like this. The scale and the offset allow me to basically change the range across which these numbers that I'm generating, the range of those numbers. So by default, if the scale is all the way up, it's going to be the range of 0 to 127, so super wide. Or I can constrain that. And then the original module doesn't have it, but I added an offset as well so that you can kind of take that range and then shift the range along the note spectrum. So the sequence is no wider now. It's just been moved. And then this right switch, which is kind of like a pretty cool little like metal switch on the real device, allows me to actually manually write some values, some sort of bits in. So I can write a 0 by going down, I can write a 1 by going up. And it allows you kind of guide where the pattern goes. So that's the result that we're getting. What's really cool is, the device by itself will give us, the out is basically the pitch, which in this thing, the real device is a 1 volt per octave CV signal. In our case, it's a signal that is on the 0 to 127 range, so representing a MIDI note. And then this pulse output will output a gate, which again happens whenever that first LED is lit. There is this expander, which will actually output the pulses for each of these lights and also for combinations of them. So 1 and 2, if I have either, or rather, if I have either of those, then I get a pulse. If I have 2 or 4, then I get a pulse. Actually, maybe it's and. I think it's and. 1 and 2, 2 and 4, 4 and 7. So these allow you to have less frequent events that are derived by the combinations of multiple outputs. And I actually have those as well coming out just as an MC signal that you can see here. And I'm sending that to MIDI, from the MIDI output from Max 1, which is then triggering some drums. And then I have this matrix that allows me to change which output goes to which MIDI note, which is linked to the drums because I'm using a drum kit, or drum rack. Pretty cool. And you can see as I slowly move this dial just off of the extreme, I get small, sometimes you can't totally control it, but I was, you're hoping for small amounts of variation. And then, like I said, I just have another one being driven over here that's sending a little bit of a mod wheel CC1 to modulate the wavetable position. All right, let's get into a little patching here. What I'm going to do is show you this abstraction. And then I will open the gen patch, but then actually we'll do a little bit of patching from scratch. So inside the abstraction here, we have not all that much, right? We have a bunch of UI controls that you can see here. And we have a gen patch. And we have, this is a waveform object, which is displaying the contents of this buffer. So if I say waveform at buffer name, and then I give it the name of that buffer, it's going to show me the contents of this buffer. And I just have it stylized so that I can actually use this, this waveform viewer as my LEDs. And then in Figma, I just made this kind of little frame with transparent circles in it, and then I just lay that on top, and that's actually how I get the LEDs, which might be worth talking about at some point in another video. So the gen patch is actually outputting. The first outlet is the pitch, and then all the rest are the various trigger outputs, or the pulse outputs. And for the first 8 of them, they're being written into the buffer and then displayed inside the gen patch. They're being written into this buffer, and then they're being displayed here. And so that's how we kind of get everything working from just from the one gen patch. So not a lot of patching in here. This is what the gen patch actually looks like. This is less complicated than it looks. And we'll rebuild this, but essentially, this is this shift register section. We'll talk about exactly how that works. Here, we're taking the first 8 stages of that shift register, and we're scaling them by these various values in order to turn the 8 bits into a number. In one of the videos that Tom Whitwell, who developed this device, made, he describes this as a DAC, digital analog converter, which makes a ton of sense, right? We have a bunch of bits, zeros and ones, that are coming out of each of these. And by scaling those different bits and then adding them together, we're turning that into some number between 0 and 255, which is pretty much what a digital to analog converter does. It just takes a bunch of bits and turns them into a voltage. Down here, we're taking the output of each of those same shift register bits, and we're just sending them to different places. So these are going to the actual output. We're actually in input 1, inlet 1 over here, we have the phasor ramp coming in that's generating basically our clock. And then over at inlet 2 here, we have just the impulses from the little right switch. But basically those phasor impulses are being multiplied by, in here, are being multiplied by the 0 or 1, and then we just output those little ramps whenever we actually have a pulse from any one of those shift register bits. And then this is where we're actually writing things into the buffer. That is about as much as I will describe now. Let's actually patch some of this up and talk a little bit about how it works. Cool. So I guess I'll stay here in this abstraction. And I'm going to create a new gen patch. All right, and I'll keep 1 and 2, and let's actually comment these. So this will be the this will be like a phasor clock, and this one's going to be the right impulse. And we might not get to actually implementing that part today, because this might be a 2-parter, or maybe we'll just do a simpler version of this. Great, and now we can actually create these connections. So what I'm actually going to do is just do a phasor over here inside the patch at 0.5 hertz, which is pretty much the same thing as 120 beats per minute. I think it actually is exactly 120 beats per minute. And then we'll do like 8. So this is our clock signal, which we're using a phasor. Obviously in URAC, they would use like a square wave type of signal, but I'm a ramp guy. And we can visualize that just for sanity's sake over here. Great. We can also grab all of this, and I'm going to delete actually that one because we already have it. But that's just our UI controls that we want. So let's talk about this shift register concept. So the shift register is basically like a bucket brigade kind of thing, where we have the first, think of, however many slots, let's say 8 slots, and a number passes into that first slot and it stores it. And then when a new number comes into that slot, it the one that's already in there, it passes on to the next slot in the row, and then that process continues. So we have, as new numbers are flowing into the first slot, or new clock pulses are coming in, that first slot is getting filled with a new number, which is just a digit. It's a 0 or a 1, and it's passing it on to the next one. So the way that we do this in Max is with an object called latch, which is a little bit like a sample and hold. If you've seen some of the fundamentals of sequencing videos, for example, the one on what, and also the one on, I believe, stash, we talked a little bit about how sample and hold works, which is simply that you would have some signal coming into the left inlet of the object. And then if you send an impulse into the right inlet, then you're going to get it will sample the left inlet and just output that. So I'm going to make a gen version of, of a what object, which is take the delta of our phasor ramp and check to see is that value less than 0. And if it is, then we're going to get an impulse, and that's going to sample our value. So now I'm just sending noise in. So let's send it to the output and see if it worked. I create a number tilde object here. And you can see we're getting a stream of values there. We can even use a scope. And if I want, I can just scale that to the range of 0 to 1. And so now we can see that we're getting stepped random values. Now, if I wanted that to be just a 0 or a 1, I could very simply just add a greater than operator in here and check to see is the value greater than 0. And if it is, give me a 1. If it isn't, give me a 0, because this noise signal is going between 0 and 1. So this is our first bit. And now to do the bucket brigade part, what we're going to do is add this object called history, which implements a single sample delay and is really useful for lots of purposes, particularly feedback. Like anytime you need to feed a signal back around, you're going to be using history, because when you think about a gen patch, the way that it works is the entire patch is happening within one sample's worth of time. And the same is true in like a JIT gen patch. If you've ever used JIT gen in Jitter, it's all one frame's worth of time. So you have a single value in gen. You have a single value coming in to each of these inlets, and everything is happening within that single sample frame of time. The history object allows you to basically look back one sample. It allows you to kind of store one sample within the patch and use that old value. So if I add a history object, and then I pass that into a new latch object, and then I send that same impulse into the second latch object, now what I have is coming from the first latch object, the new noise generated digit, and coming from the second, I have the old one. So you can see we're getting two different values there. So this is our shift register, and we can replicate this several times over. So I'll just make, let's do 8. So that's 1, 2, 3, 4, 5, 6, 7, 8. That's 9. And then I'm just going to connect these. Great. And then we need the impulses. Right. So each time we get an impulse, each of these is going to pass its contents on to the next. Now, what is really cool about the Turing machine, and the thing that kind of makes it awesome, is that this final step actually loops back around to the beginning. And that is where this so-called big knob has its effect on things. So this big knob controls whether or not this 0 or 1 stays the same as a 0 or 1 or gets flipped, gets inverted. If the knob is all the way to the right, then we just get a loop of the input to the output. We get a loop where the last value is just send right back into the beginning, and we get a constant loop. If we're in all the way to the left, then we always invert. So we always flip around that value, turning zeros to ones and ones to zeros. And then if we're anywhere in the middle, we have some probability deciding whether or not that happens. If I'm further to the left, I'm more likely to invert. And if I'm further to the right, I'm more likely to not invert, keep the value the same. And if I'm in the middle, I'm equally likely to invert or not invert. So let's actually build that. I have to pull up my notes here. I'll do it on a separate screen. So we're going to take the output here of the final bit. And we're going to create a param object. Actually, before we even take that, we're going to create a param object and we're going to call it big knob. Because I'm going to be sending this message big knob with some value into the object. And so when I send that message, the value is going to come out of this particular operator. And I like to give my param objects like a little bit of color so that I can quickly identify them. Okay, and then we're actually going to take this noise, and rather than passing it straight into the first bit, what we're actually going to do is check to see, is the noise value that's coming in less than the param object, the param object's output. And then we're going to take the result of our final bit, and we're going to subtract that result, which is going to be a 0 or a 1, from our final bit, which will also be a 0 or a 1, and then we're going to take the absolute value. And why are we doing all this? Let me just show you an MSP over here on this side really quickly. So if I have a couple sig objects here, and I connect toggles to them, and then I subtract. And I could do this in Max too, but it's sometimes nice to use MSP because you always know that both inputs will be hot. And I'm just going to create a number object here and get the output. So let's assume this is going to be my control. This is what's being derived from the big knob, the one on the left here. And then this is the test, I guess we would call it. It's coming from that last bit. So if my control is on and my test is 0, we're going to invert. We're going to go from 0 here to 1 here. If my test is on and the control is 1, then we'll get 0. If my control is off and my test is 1, I'm going to get -1. And if it's 0, I'm going to get 0. So now if we take the absolute value of this, what this now means is that a 0 here keeps the value, and a 1 here inverts the value. So 0 means don't invert, 1 means invert. So that's what we have happening here. We take the noise, we check to see, is the noise value less than the big knob value? So if I'm way over here to the left, then it's very likely going to be less than the big knob value, which means we'll get a 1, which means that we'll invert. If I'm very far over here to the right, then we're more likely to get a 0, which means that we won't invert. And then we're simply going to pass that around into the first latch object using a history operator, because we need to do that in order to, do this feedback loop. And the result that we're going to get, if we if we were to look at all these outputs, is basically this looping figure. And I'm trying to think about how we can, so let's actually do the part now where we make the pitches. So we'll turn this now into we'll do the DAC thing. We'll turn it into a number. So I'm going to do 128 times 64, and these are just powers of 2. So we have 2 to the, over here on the right, we have 2 to the 1, or sorry, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 3 is 4, I'm sorry, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 8, and 2 to the 16. Oh, and actually I had an error, which is actually in my other thing too, so I'll fix that, but it should be, rather than this being 128, this is 64. So an 8-bit number doesn't give us between 0 and 255, and it gives us between 0 and 127. Cool. So now we're actually building that value, that looping value. And we can now take this scope and change its range so that it goes from 0 to 127. And now we can see we have these moving values. If I also then just take to the second output, our first bit times our incoming ramp, we can then get a ramp for each of those each time that first bit is activated. And then if we wanted to, we could do just like I have in the other example and send that to like an MC MIDI player, which takes a ramp to its first inlet and a MIDI note value to its second inlet, and creates a MIDI note. And so that's what we have happening back in our main patch. We have coming from the first outlet here, we have some MIDI note value. And then in this particular example, I'm taking all of the outlets of all of the bits here, and I'm just packing them into a MC signal. So that's what all of these are. Let's now do the scale bit, which is pretty simple. So we'll make another param object. We're going to call this scale, and we're just going to it'll be a value between 0 and 1, and we're going to multiply that value that comes out by that. Sorry, I had to think there a little bit. So that's really simple, all we're going to do. And then, we probably want to quantize that. So I'm just going to use a floor operator here so that we don't get any floating point numbers. We always get a whole number. And then this is where I felt like the offset actually did make quite a bit of sense, because if we're talking about using MIDI here, right, like, by default, I'm going to get this really super wide range of MIDI notes between 0 and 127. If I scale it, then I can kind of force that down to be maybe, I don't know, an octave, 12 notes or 6 or something. But if I just use this by itself, I'm only ever going to get, if I have say 10 notes, I'm going to get between 0 and 9, which is not particularly musically useful. So we can also add another one here, which we call offset, which is going to allow us to basically shift that 10 or however many across the range. And the way that I did that was basically multiply the offset, which is also going to be between 0 and 1, by the number of total possible steps in our range. And then we will take we'll take the scale value times 32, and we'll subtract the offset times 28 from that, and then we'll add together our scaled value and the offset. And I kind of figured this out through trial and error, but what I'm trying to basically do here is get to the middle of the range. So if we have, maybe this should be a 64. Let me think. I suppose this should be a 64. I guess we can test it. So let's see what happens. So we have the scale. Let's set the scale to 100. I don't know, something in the middle. So we're getting these values that are kind of hanging around the low end of the spectrum, right? But then if I move the offset halfway up, then I'm kind of in the middle. And if I go towards the top, yeah. So basically I'm kind of setting what's the midpoint, right? So I actually have to fix that in my other patch. I don't think that's exactly correct. So that kind of gives us something that's a little bit more musically useful. So the other things that this device is capable of doing is a couple of things. So, well, one thing to call out is the big knob has this pretty cool capability, which is that if you turn it back the other way, it doubles the length of the sequence. And that's actually already baked in to the patch that we have here. Because what's going to happen is it's going to run through the patch, and then it's going to invert the whole, or so run through the sequence of ones and zeros, and then it will invert them, and then it will invert them again, so it'll go back and forth, so that makes the pattern twice as long, which is super, super cool. Like, really, really beautiful, elegant little algorithm here that just does so much with so little. It also has this length dial, which lets you decide between 2 and 16. So in fact, the shift register is actually twice as long. So what we need to do is this. However, the first 8 are the only ones that are actually used to create the pitch values. And then the way that the length is determined is we basically decide where the loop back occurs. Does it occur, 8 steps in? Does it occur 16 steps in, or something in between? And there are 8 options. So there's, if we go back and look at the thing, 2, 3, 4, 5, 6, 7, 8, 12, 16. So that's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 options. So what we're going to do here is create a selector object with 8. And we'll do a param length. And the value that we're going to be getting here is not going to be 2, 3, 4, 5, the actual length as we understand it. It's just going to be the position of the knob between 0 and 8, or 0 and 7 rather. And so what we can then do is just take 2, 3, 4, 5, 8, I think. 2, 3, 4, 5, 6, 8. 2, 3, 4, 5, 6, 8. And then 12, which so we have 9, 10, 11, 12. And then 16. And do I have an extra that I'm not supposed to have? Am I doing something wrong? 1, 2, 3, 4, 5, 6, 7, 8. So I have 2, 3, 4, 5. Wait. 1, 2, 3, 4, 5, 6, 7. I didn't have enough of these. I only had 7 when I needed 1, 2, 3, 4, 5, 6, 7. So I see the whole mistake that I made where I thought that I had done it wrong before, but I'd actually done it correct, which is because this was only 7. 1, 2, let me count again. 1, 2, 3, 4, 5, 6, 7. Yeah. All right. So I need to fix this. And by the way, you can see that we're just connecting all of these together to the same inlet of this multiplication object. And so that's because that'll just add them up, same as in MSP. And now I need to fix my scale and offset stuff. So I think hopefully all I really need to do here is just multiply my scale value by 0.5 because I want to half that value between 0 and 255 to the range of 0 to 127. So if we test that by turning the big knob, and we start to get some random values, and now if I move the offset around, it looks like it's generally working. I think it's correct. Someone can tell me if I'm wrong. Okay. So now we have the 2, 3, 4, 5, 6. So let me just delete these and we'll redo this. 6, and then 8, and then 12 is 9, 10, 11, 12, 13, 14, 15. So we need another one of these to make 16. There we go. Cool. So then rather than taking this here, we're going to take that output. And so that length parameter basically determines where the looping starts and determines the length of the pattern. So you can see now if I pull this length dial way back to 2, it looks as though we're getting 3 values. Oh, because we had random. Oh, well, one thing I had to do is add 1 here to the length because I'm getting a value between 0 and 7, and really I want a value between 1 and 8 to pass into the selector, so that's probably part of the problem. Let's call that the problem. And let me just look at what else I have going on here in my patch. So the one thing we haven't implemented, and we're not going to do it right now, is this write impulse thing, which is a little switch. Maybe we can get that to that another one, but what I really wanted to show you, oh, and by the way, error, we have to connect these impulses. What I really wanted to show you is kind of how these shift registers work and how like they're super duper cool and can be used actually for tons of different sequences, like uses. So if you can imagine other ways of using this, then, you know, build it. I know there's like the mutable instruments marbles is really basically a derivation of this same kind of algorithm. And there's other sequencers like one called Clay and some others that that implement this. And by the way, if you want more information on how to build one of these shift registers, I highly recommend the Go book, Generating Sound and Organizing Time, which Cycling 74 put out recently and is by Graham Wakefield and Gregory Taylor. I learned how to make a shift register from that book, and in fact, I learned how to like do gen period from that book. I wasn't doing any gen before that, and now I used a lot. It really opened up the world of gen for me. So let me know how you're enjoying this. Let me know if you have any questions, and I'll see you next time. Bye.